Hello, everyone. Welcome back to the part three of this lecture on uh, distributions of transformations. Uh, in this part, we are going to look at few more examples, and then we will continue to the delta method, which we use to get an approximation for the variance of a transformed uh, transformation. Right. So the first example that we look in this part is a very useful result actually. Even though I mentioned it as an example, you can use it as a theorem also. So let's look at that. Let U be a uniformly distributed random variable in the interval 0, 1. Suppose fx is a continuous cumulative distribution function of some random variable x, and define y to be the inverse of this cumulative distribution function evaluated at capital U. Then we are going to find out the distribution of y, and the result will be very, very interesting and useful. Notice here again, I'm defining y to be fx inverse evaluated at capital U, where U is a random variable, uniform random variable. So this whole thing is a random variable. Fx is the cumulative distribution function of random variable x. Then always fx inverse exists. So we can uh, talk about fx inverse u as a random variable. Okay, so let's look at the distribution. Let's derive the distribution of y. Okay, so let's look at the cumulative distribution function of y at some value simple y. So by definition, this is equal to probability y less than or equal to simple y. But we can write down now y in terms of u because we have defined y to be fx inverse u. So just replace y by fx inverse u less than or equal to y. Now, since fx is continuous and strictly increasing on its support, especially non-decreasing function, when you consider the continuous random variable, it is strictly increasing. The function fx inverse is also strictly increasing. Therefore, uh, this condition or this event, fx inverse u less than or equal to y, implies u less than or equal to fxy. It goes both ways. This implies this, and this implies uh, this, right? Therefore, we can replace this event as by this event. So the cumulative probability distribution of y evaluated at simple y will be then probability u less than or equal to fx y. But now remember that this is the cumulative distribution function of u by definition, right? This is the cumulative distribution function of u. So I can write down one more line to make it clear. So this is actually f of u evaluated at fx y, right? Fu cumulative distribution function evaluated at this real number, fxy is a real number. But because U has a uniform 0, 1 distribution, Fu at some value U is equal to actually U. right? This is the random variable capital simple value u. FUU is equal to u when capital U as a uniform 0, 1 distribution. So therefore, according to that, FU evaluated at fxy should be the same as fxy. So that's why we have this expression here because of this fact. Okay. So let me delete my annotation there. So therefore, what do we get now from here? This says Fy is the same as Fx at y, right? The cumulative distribution function of y evaluated at value y is the same as cumulative distribution function of x evaluated at y. So that implies that uh, the distribution of y is the same as distribution of x. Distribution function of y is the same as distribution of x. In other words, y has the cumulative distribution function fx. So what is the use of this? We can use this theorem or result to derive or get the data from any distribution starting with a uniform distribution. Right? Suppose you start with some uniform data, U, and suppose you want to get the data from some distribution with CDF fx, a given fx. So what you have to do is transform these uniform random numbers using this random this transformation and call it y, for example. So you'll have set of y values now transformed using fx inverse and calculated uh, evaluated at all the u values coming from the uniform distribution. Then the resulting values will have the same distribution as the distribution of x. In other words, these y values will have the cumulative distribution function fx. So that's like generating data from fx, starting with uniform 0, 1 random numbers. So that is the importance of this particular result. It's very useful. So accordingly, starting with uniform 0, 1, you can get the data from any distribution you want, as long as you know the cumulative distribution function of the distribution from which you want the data. Right? Once you know the cumulative distribution function, of course, you can get the inverse cumulative. Right? As far as R commands are concerned, the cumulative distribution function can be calculated using names with P, starting with P, like P norm, P exponential, P gamma, and so on. The inverse cumulative distribution function can be calculated using the function starting with Q, Q norm, Q exp, Q gamma, and so on. Right? So that will be given by the quantiles. Quantiles. Right. So this theorem is therefore very useful to get data from any distribution with a known CDF, starting with uniform 0, 1 data. Because in any computer, using any computer, you can always generate data from the uniform distribution. But there may be, your package may not contain a function to generate data from a particular distribution that you want. For example, if I want to generate data from a Pareto distribution, there's no well-known function written to generate data from a Pareto distribution as far as I know. But using this theorem now, we can generate the data from Pareto distribution because we know the CDF of a Pareto distribution. Right. So that is the importance of this result. Okay. So therefore, it's very clear now. Starting with some uniform data, uniform random numbers, we can also generate data from a normal distribution, right? So that means you can normalize. And also in the previous part, we learned another important theorem that we can convert the data from any particular distribution into uniform also, right? So combining these two now, a very important result comes. Suppose you have some data from coming from some uh, uh, distribution of X. Using these data, suppose you want to convert these data into normal data, right? Normalize the data in the variable X. You already have some data from a random variable X, and you want to convert them into normal data, right? We call it normalizing. So how can we do that? First, we can transform the data in the variable X into uniform using probability integral transform that we discussed in the previous part. Then once you have those uniforms, then you can convert those individual observations into normal distribution using the result that we discussed a few minutes ago. So that's therefore is going to be very useful. You can convert your X data into Y, where X has some non-normal distribution, but Y will have normal distribution. So is it possible to normalize any continuous random variable X with a non-CDF X? The answer is yes. So what do you have to do? So first of all, get the X data and then apply this probability integral transformation. Say U is equal to fxx. So here you have to know the distribution of X. And then U will be distributed with uniform 0, 1 that we discussed earlier. We have proved this. And then now let us define a new random variable Z. For example, inverse of the standard normal distribution evaluated at these U. So from those, you will get some Z values, which are standard normal. The distribution of Z will be standard normal. This is the inverse of the standard normal cumulative distribution function, right? So Z will be standard normal. So that's a one particular example where you can convert whatever the data you have for the X variable X, random variable X, you can convert them to standard normal data. But now suppose you don't want standard normal data, you want the data, normal data with some mean mu and standard deviation sigma. Then you can go further one step by saying Y is equal to sigma times Z plus mu. So this will convert those standard normal data into a normal data with mean mu and standard deviation sigma. So in the case, Y will be normally distributed with mean mu and variance sigma square. So that's a pretty interesting result and very good and very useful result. Right. So let's look at an example. Suppose you have some data from an exponential distribution with rate parameter lambda, right? Suppose we have to know the lambda in this case, but so in general, suppose the rate parameter is lambda. First of all, we can come up with the theory and then use the corresponding lambda when you are generating practically, right? So write R code to check the analytical derivation via simulation. So this problem was taken from the book, textbook. So suppose we have, assuming that you have some exponential data coming from an exponential distribution with parameter lambda, then write a code to, that means write a code to do the previous steps, right? Write a code to check the analytical derivation via simulations, right? So Suppose X has a exponential distribution with parameter lambda. So its density function is given by this one. This is well known. And the CDF, of course, we can obtain. CDF will be given by this function. When x less than or equal to 0, the CDF will be 0. And when x greater than 0, it will be given by this. You can easily get that by integrating the density function from 0 to some value x. Right. So therefore, if because x is given by this expression, uh, when you apply the first probability integral transform, u is equal to fx capital X. Right. So fx simple x is equal to this expression. Therefore, fx capital X is equal to 1 minus e to the power minus lambda x. Then, of course, according to the theory, we know that u should be distributed as a uniform 0, 1 random variable. Right. We demonstrated this thing in the previous part by generating some data. Right. And then take the define Z to be phi inverse U, where U is these data here. So we can, for example, say Q norm, right? Phi inverse is given by Q norm function, Q norm U, right? First of all, here we are using Q norm with mean 0 and variance 1, standard deviation 1. So that's what this capital pi inverse is, right? The inverse cumulative distribution of a standard norm distribution. So then theoretically again, Z will be, as we explained earlier, Z will have a normal distribution with mean 0, 1. Then if we specify the mean and sigma standard deviation we want at the end, then we can convert again these Z values into Y by this transformation. Then Y will be normally distributed with mean, mu, and variance sigma square. So therefore, if I write down the whole transformation by combining these three, Y will be sigma times Z, where Z is this pi inverse, U is equal to this thing. So therefore, the whole transformation and then plus mu, right? So therefore, the whole transformation can be written in one line like this. Y is equal to sigma times pi inverse evaluated at 1 minus e to the power minus lambda x plus the mu. Right? So that will be the normalizing transformation from exponential random variable with rate parameter lambda into a normal random variable with mean, mu, and standard deviation sigma. So let's write down an R program and generate some data according to this transformation and see whether actually the exponential data transforms into a normal distribution. So what I'm going to do is I'm going to consider a particular lambda here. I'm going to take lambda equal to 0.01. And suppose I want to convert. So I will generate some data from an exponential distribution with lambda equal to 0.1 first. And then finally, I want to convert all those observations into normal data with mean, say, 50 and standard deviation 5, right? So what I have to do is I have to first generate some data, say, for example, because I want to draw a histogram and get the shape nicely, I will consider a large number of observations. Otherwise, the histogram will not look like the actual distribution, right? If you generate only very few observations. So let's consider 10,000 random numbers from an exponential distribution with lambda equal to 0.1. So x is equal to REXP 10,000 with this lambda. So that will have exponential data. Then I am just using the complete transformation at once. Y is equal to sigma times Q norm, that is that capital pi inverse function, Q norm, 1 minus exponential minus lambda times x plus mu. So what I am applying is this transformation here. So Y. And then I am going to draw the two histograms, histogram of exponential data as well as the histogram of the transform data side by side to see the difference in the distributions. Of course, the first one should look like an exponential distribution. The second one should look like the normal distribution with mean 50 and standard deviation phi. So I get the, first of all, divide the screen or the graph window into one row and two columns, and then draw the histogram of X and histogram of Y side by side. So this is what I get. So you can see that this actually looks like an exponential distribution when you smooth it, a density function. This is a normal distribution again, approximately with mean 50, right? So you can see that, I mean, this is not a proof. This is a demonstration, right? You can demonstrate what happens actually when you apply that particular transformation to the exponential data. The data are converted into normal distribution with mean 50 and standard deviation 5 here. So you can see that actually it works like that. Okay, so I'm going to end the discussion of that transformation part there. So what we looked at was, first of all, we looked at how to transform. If we have a one-to-one transformation from X to Y, we derived a formula actually to get the probability density function of Y. Right? So either you can directly apply the formula that can be used only if your transformation is one-to-one. That means either uh, monotonically increasing or monotonically decreasing, not both, right? Then also we looked at some examples. There also I considered some examples where the transformation is not monotonic. In that kind of situations, it's easier to first derive the cumulative distribution function of Y and then convert it into the density function by differentiating the cumulative distribution function. I showed you an example in the previous part. And then we looked at a very useful and interesting result, that is the probability integral transform. From that, you can convert the data in any distribution into a uniform data. And then finally, here I showed you how to convert, get the data from any distribution, starting with the uniform distribution, right? So now we are going to look at the last part of this lecture, that is called the delta method. Delta method. Now we use this delta method mainly when you want to get the expression for the variance of a transformation of a variable. Right? So for example, if I'm interested in some gx, where x is a random variable, I'm interested in gx, I want to find out the variance of this gx. This gx can be quite complicated function of x2. Right? So if that is the case, deriving the expression for the variance is quite difficult. Getting the exact variance is almost impossible in most cases. Right? So what we are going to do is get an approximate expression for the variance of that kind of gx transformations of x. So the delta method approximate the variance of a nonlinear function of a random variable. Of course, if it's a linear function, we don't need any of these things. We can directly get the variance exact formula. This is important when the transformation is nonlinear. This method only requires evaluating the first derivative. So therefore, this method is very popular. That's why it has a name also. It's called delta method. Right. So let y is equal to gx. X is a random variable. G is some transformation. And generally here we are interested in a nonlinear transformation. Suppose you want to get the variance, expression for the variance of y, but theoretically it's very difficult to get the exact variance. So we want to get an approximate expression for the variance of y. Right. So if we know the density of x, of course, we can write down the expression, theoretical expression to get the variance of y. The problem is usually it will be difficult to simplify that. So what will be the expression that you have to simplify if possible to get the variance? Of course, that is the expected, if you are interested in the, so let me write down here one line before this. Mm, So we know that the variance of g of x is equal to expected value of g of x whole thing square minus the expected value of g of x whole thing square. This is coming from this expression. If you remember, for example, the variance of x is equal to expected value of x square minus expected value of x whole thing square. So instead of x, now we have gx. So the corresponding equation will be like this. So therefore, expected value of gx square can be obtained from this expression. G square x is the same as gx whole thing square times the density function of x. That will give you this part. And this part, of course, given by gx times fx dx. And then we need the square term here. So this is the expression that we'll have to simplify if you have to get the variance of gx exactly. But unfortunately, simplifying this expression will be quite difficult, especially when gx is a complicated function and fx can be also a complicated density function. So simplifying this thing will not be that easy. So therefore, instead of trying to get the actual expression or the exact expression, what we'll try to do is get an approximate expression for this. So variance of gx. So to approximate the variance of y or the variance of gx, what we do is we first of all consider the tail expansion of gx around the mean of x. Suppose the mean of x is mu, expected value of x is mu, right? So uh, we are going to consider only the up to the first order term, right? We are going to neglect all the terms after first order, second order, third order terms. So therefore, gx will be approximately equal to g mu plus x minus mu times the first derivative of g evaluated at this particular mu, right? So this is the first order approximation to gx using the tail expansion. Right. Now, what I want is the variance of this gx. Variance of this side will be equal to the variance of this side. But notice that g mu is a constant and g dash mu is also a constant here. Only random variable here is x minus mu here coming from this part. So the variance of this whole thing is like variance of a constant plus another constant times a random variable, right? It's like variance of ax plus b, right? So we know that is equal to a square times variance of x, right? So if I apply that standard result here, the variance of gx will be equal to square of this quantity times the variance of x minus mu. But we know that variance of x minus mu is the same as variance of x. So therefore, we easily get an approximation for the variance of gx as square of this term, that is g dash mu square, times the variance of x. So you start with x, you know the density function of x, for example, or you know the variance of x, therefore, uh, and you know g, so therefore you can get the g dash, the first derivative, and you know mu, therefore you can get an expression for this. Variance of x is, we know the expression, therefore we can easily get the expression for the variance of gx. And if you take the square root, then we can get the standard deviation. Standard deviation of y, that is the standard deviation of gx, will be equal to the absolute value of g dash x times the standard deviation of x, right? When you take the square root of this square term, we don't consider the negative value because the standard deviation, for the standard deviation, we get only the positive value. So that is the that is called the delta method, because it involves the derivative here, and derivative is written in terms of some delta notation usually. That's why I think it's called the delta method. But it involves the derivative of g, first derivative. Right. So advantage of this delta method is that this approximation is valid for any distribution of x, right? Of course, not for all. There can be some situations where mu is not defined, like in a Cauchy distribution. So excluding that kind of uh, special type of distributions for which the mean doesn't exist and the variance doesn't exist, for all other random variables with other distributions where the mean and the variance exist, this result can be used regardless of the actual distribution. So as long as we know an expression for the variance of x, we can get this approximation for the variance of gx. Let us look at one example as the last item of this lecture. Right here, we are going to look at another problem from the book. So the book says there are in many real life problems, the problems are formulated in ambiguous language. That is actually true, right? Usually when clients come to us from different fields, they are using different types of technical words. And sometimes the question of interest is not very clear in most of the situations. We have to first understand the question. So the way that they express the question and the way that we understand the question have to be the same if we want to deliver a correct solution, right? So anyway, this problem shows you some possible difficulties arises in interpreting the question. And if we interpret the question in a way that is meaningful, then we will be able to answer it meaningfully, right? So let's look at this problem. The radius of a circle is measured with 1% error. Radius is measured with 1% error. What percentage measurement error does it imply for the area? Right. So this is the question. But if you read the question, the radius of a circle is measured with 1% error. What does this error mean here? In different people can actually interpret the error in different ways. Of course, in this case, the radius of this circle is a fixed value. We don't know the radius. That's why we are measuring it. So suppose the radius is some unknown quantity denoted by rho. Suppose the observation is denoted by x, the measured value. So in that case, the error will be x minus rho, the error. So is this problem telling that x minus rho is 1% of rho? Is that what it's saying? Or is it telling something else? Because some people sometimes use the word error to denote the standard deviation of some random variable also. In most of the engineering, physics, and that kind of situations, or even biology, some people use the word error to denote the standard deviation of some random variable. Maybe this person is referring to that also, right? So the book has answered, taking the second meaning for the word error, right? So let's look at that answer. It says the formulation of the problem lacks clarity, right? So in order to answer it precisely, we have to know what the client means by the error. Then only we can answer it precisely. But the book takes this meaning here. As I mentioned, we are going to assume that there is some unknown radius. Let us denote it by rho. And the measured radius r can be considered a variable. Of course, after measuring it will be a value, but before measuring it, it can be anything around the value rho. So in that case, it can be considered as a random variable. Therefore, I'm going to denote it as by capital R, right? So maybe this client is telling that measurement with 1% error means the standard deviation of R, sigma R is equal to rho divided by 100. So sigma R is taken as the error, and error is equal to 1% of the actual value. So that is another way to interpret it. If that interpretation is the same as the interpretation of the clients, the answer will be correct here, right? The area of the circle, if the radius is equal to r, the observed value is r, we will calculate the area as pi r square, pi r square. So that's actually a transformation of r, pi r square. So therefore, if you want to get the percentage measurement error for the area, and if you take the error to be the standard deviation, what we are interested in, the standard deviation of A divided by the actual area which is unknown times 100, right? This will be the error relative to the actual area times 100 will give you the error percentage in that case. So therefore, we will need the standard deviation of pi r square, which is pi r square is a transformation of r. So if you know the standard deviation of r, we can apply the previous result to get the standard deviation of pi r square approximately, right? So therefore, according to that result that we just derived, standard deviation of pi r square will be approximately equal to the derivative of this function with respect to r times the sigma. The function is pi r square. So that is g of r in this case. So you have to calculate it at mu, right? So if r is the measurement, we can expect r to be distributed around rho. Rho is the actual value. So therefore, r will be rho plus or minus something. Therefore, it's meaningful to assume that expected value of r is equal to rho. So according to the result, that is the same as mu. So what we need is g dash mu. When you calculate the standard deviation, g dash mu times standard deviation of r. So this is g dash mu, right? 2 pi r, and then mu is equal to rho in this case. Time standard deviation r is rho divided by 100. So this is the standard deviation, this part. So if you substitute into this expression, then the value that you get is 2 here, right? You will get 2 when you simplify this. So that means the percentage error of the area, right? If you take the meaning of error to be the standard deviation, then it will be 2%. So if you take the meaning of error in the client's problem to the standard deviation of R, for example, then the error in the area will be 2%. If there's 1% error in the radius, uh, error in the area will be 2% of the measurement error for the area, right? So that's the end of this lecture, where it has three parts, right? Part one, part two, and this is the part three. So in this whole lecture, we discussed mainly two topics. The first one is distributions of transformations of random variables. There we discuss some very important and interesting results. And then finally, we discuss how to obtain an approximate expression for the variance of a transformed random variable. Okay, so that's the end of this whole lecture on transformations and the delta method.